So my talk today is about two terms. So over the years, I've become frustrated with terminology. So streaming is the way to go, or microservices or whatever, but those are the terms that we have, so we have to kind of talk about them in that context. What I want to try to do in this talk is talk about the reality of those concepts and what they mean under the covers, and how we can digest these different ways of building systems and reasoning about data. If you had a chance to attend Colin's keynote, Colin works for Tesla, in the energy sector. He used to be a company called Solar City, and I was cutting my chops in the energy industry too. And the thing about the energy industry is that it supports people's ability to function, right? It gives you hot water, it gives you lights, it gives you the power to your computer. So it's kind of interesting if you work in that type of industry, or maybe medicine or something else. The impact of your application failing has a little bit of a different reflection on reality than, say, if you're running an HR system or something like that. So the pressure and kind of like the expectation's a little different, because if your stuff fails and lights go out, things don't work. So, but just like any other industry, the energy sector was behind the times too, right? So they needed to come up to speed and figure out new ways. And ultimately what it came down to is to embrace distributed computing. So I'm going to give you the summary of this presentation. This presentation is about distributed computing, which essentially is embracing things like asynchronicity and parallel computing, and understanding that that environment is different than perhaps the environment you were trained in. So I was trained in your standard monolithic style of building an application and such, and they work very well for the things that they work on. But when you get into this vast amounts of data that you have to deal with and the expectations of SLA and uptime and all these other things, reality changes. And at least the way that I was taught, I go all the way back to a mainframe, doing IBM DBDC and all that fun stuff, vSAM data sets. And the way that I was taught, that didn't necessarily translate into what we're doing now. So hopefully at the end of this talk, I will have been able to convey that idea. So just a little bit about me. My name's Duncan. Right now I work for Lightbend. I'm the Director of Solutions Engineering, and I did a bunch of other stuff. I've been at Lightbend for 4 years, and then the last one I was a VP of Engineering at my the energy company I worked with, and I've been doing computer science type stuff for about 25 plus years, so I guess I like it. Sometimes I wake up and think, maybe I should have been a potato farmer or something different, but so us, you guys know about us, right? We're all about reactive. So these principles behind reactive is another one of those words that kind of gets this interesting context to it. What I'm going to tell you is that reactive, right, this next image, this is all about distributed computing, okay? That's what it means. So when you see the word reactive, at least from Lightbend's perspective, right, because there's React.js and a lot of different technologies that use the word reactive. When we talk about reactive, we're talking about building a distributed system, right? A system where you have, we call them nodes. We're talking Java, so JVMs, anywhere from 5, 10, 15 to several hundred or several thousand nodes working together in concert to bring a solution. And so those 4 boxes, and I'm sure you've seen this, but this image it really is super powerful. This is a perfect example of an image is worth 1,000 words. At the top, we have the most important principle. We have to be able to respond. Regardless of my situation, I've got to be able to come back with an answer. Now, it may not be the answer that you want, but at least by responding, I've shown you respect, right? Just think about it from a human perspective. If we're doing something together and you ask me, how many people have you ever asked somebody a question and they don't answer you? And you're looking at them thinking, did you even hear what I said, right? Anybody ever have that happen to them? I've had it happen a lot. So responsive is crucial. Wars get restarted because we're not responsive. In order to be responsive, we have these 2 other pillars, resilience and elasticity. Elasticity is easy, scaling in and out, up and down. However, resilience often gets confused with fault tolerance. Resilience is not fault tolerance. Resilience is self-healing. So it's the ability to take a corrective action on your own accord and correct your course. This becomes really important, we'll talk about later in the presentation, about something called a feedback loop, which comes from classical engineering. If you're any electrical engineers in here or mechanical engineers, you know that term really well. In software engineering, it's relatively unknown, unfortunately, but it's a crucial point of building a successful system. And then we believe at the bottom of this, in order to be able to facilitate the two pillars that hold up responsiveness, you have to have some type of loosely coupled design, right? With location transparency and things like that. So how do you get that? It's by being message driven, right? And then that brings in all the questions about guaranteed message delivery and all these other things that people complain about with this type of architecture. There are reasonable complaints, but a lot of it's due to a lack of understanding of the philosophy behind distributed computing. So, you know us, we made Akka and Scala and Lagom and Play, these different technologies. We actually purchased Play a while back, and under that we have this thing called the Enterprise Suite, or we can now call it the Enterprise Suite 2, which is a core set of commercial offerings that we add to kind of boost distributed system type stuff. One of the examples, two of my favorite, is Cinnamon, which is our monitoring tool. I was on the Cinnamon team for several years. And also our split brain resolver for pulling or solving the problem when a cluster breaks in half. So, and then we also have some additional products that we have. So this is kind of like our fast data platform, and we'll talk a little bit about that, and that's ultimately streaming is what we're going to end up talking about. And there we provide a bunch of different tools that kind of facilitate the orchestration of that, and also something that we're coming out with called pipelines, which is kind of an interface to allow you to reason about and piece these puzzles together without having to go real deep into code. All right, so enough about that. What we're going to talk about microservices, obviously. We're going to talk about something called promise theory. Has anybody heard of promise theory? Okay, good. Excellent. So we're going to talk about promise theory because I think that's foundational to understanding how to build distributed systems. We're going to talk about event sourcing. We're going to talk about CRUD. We're going to talk about fast data or streaming. And then we're going to talk about feedback control. And so what we're going to do on this little journey is we're going to talk about these things, and then we're going to kind of put together a metaphor of what a fully built out distributed platform might look like. So first, microservices. Anybody in here not heard of the term microservices? That's good, right. So really it stemmed from things like Agile and different things like that. And the idea was we want to be able to provide an environment where the folks who are building and reasoning about applications can do it in a manner where they're not dependent on each other, okay? And so one definition, I think this is a reasonable definition, you know, you have multiple autonomous teams which are organized to basically be able to develop and manage and deploy independent of each other. And I think that's a great textbook definition, but I don't think it captures what a microservice really is supposed to be, right? I think this next definition is really what it is. Right? It is a system of autonomous, collaborative, distributed services. And the two words in there are very, very important, autonomous and collaborative. So autonomous is a Greek word, comes from a Greek word, autonomy, which means self-governing. So what that implies is that your microservice that you're building is its own ruler. It's its own law, right? So it's going to take care of itself. If it has a problem, it's going to fix itself, and so forth. And then it also is collaborative. It works with others in order to, you know, deliver a bigger solution, right? A bigger promise or what have you. So I just want to go back one more time to that. Those two words, I think, are absolutely crucial. In fact, if I was interviewing somebody and I would ask them what is a microservice, this is what I would want them to tell me. And because that shows me that they understand the purpose behind it, right? It's designed such that it can fulfill the reactive manifesto, right, on its own. So that means if I depend on an external service to give me data, that could be problematic because if that external service is down, then I may not be able to deliver, right? So what does that mean? I may have to keep a copy, a cache of that data locally in case that external service goes down. So in looking at microservices, right, what are some of the key tenets? We're going to talk about promise theory, but I would say apply promise theory to your design. Keep your services small, right? One of the best things to learn is, I learned this when I first started programming. My boss came in and he said, Duncan, you write too much code. Keep it small, compile, keep it small, compile, keep it small, compile, right? And so that way you can easily reason about what you're doing and testing it. And I think that is crucial, especially when you start doing more complex, types of programming. Cluster, obviously for resilience. And another thing which I find interesting is, as engineers, a lot of times we think we determine what the consistency model is going to be or what the load time is going to be and such like that. We don't, right? It's actually, what does the SLA say? So if you work 100 hours to solve a problem to make your service run in a second, but the business doesn't care about that, all they care about is that it runs in 10 seconds, then you got to ask yourself, did you use your time wisely? So understanding what the SLA is, like Jamie talked about yesterday, reactive is a product, right? That's real important for us to understand as engineers as well. So, and then polyglot persistence. Use whatever store makes sense for the particular service that you're building. And honestly, that's like different than the way we were, or at least the way I was trained. Everything was, dry. Don't ever repeat anything. Make sure there's not another line of code anywhere. Your database should never have duplicate data in it and all these kinds of things. And what I'm saying is the exact opposite of pretty much everything I learned anyways. So some of the key things behind microservices are, and Pat Helen, this comes from Pat Helen, but the data that you have locally inside your microservice that you have access to, that really is your reality. If you were at Colin's speech yesterday, someone asked him a great question, and it was, how do you get rid of the noise? How do you deal with these things to make sure you give the appropriate answer? And the response is, you only know what you know, and you don't know what you don't know, right? So when that question is asked of you, you have to make a decision. Can I answer it, or can I not answer it? And if I can answer it, then I can say, look, here's my opinion of this at this moment in time, right? But because of surrounding circumstances, it may not be 100% accurate. So that's the way you have to deal with it. The fallacy of, I'm going to build a system that's never going to crash or is always going to give the right answers is exactly that. It's a unicorn. It doesn't exist. So understanding the only data that you have that is, as far as you're concerned, that is real is what you currently own. Data that comes from the outside is always historical. It's always historical. When you make a call to a service, you get a piece of data back and you process it. By the time you're done processing it, it could have changed out there. And you have to understand that reality and accept it. And then when you ask a question before you get the data back, that's the future, right? So you have past, present, and future. Your present is now your data. The past is any data you receive from the outside. And the future is when I ask a question and I'm waiting to get an answer back. So the reason these concepts, I think, are really crucial, and it may sound like obvious, but they're really crucial to kind of embed that into the way that you think, right? Kind of like live it. I would almost say distributed computing is almost a lifestyle. It's not a philosophy. I believe it's so different from what we've been classically trained in that we really have to step back and think about it differently. So, as he says, regardless of the storage medium, our view of state is always of the past, right? The whole, do I use CRUD or event sourcing? We'll talk about it in a minute. It depends on what your state model needs to be. If you need history, then you need to do event sourcing. If you need only current state, then CRUD's perfect for that. So, picture-wise, when we talk about building distributed systems and owning your own data, On the left here, you'll see the classic design where you have a multi-tiered application, and then it's tied to some type of database, whatever that may be. On the right, we have independent, autonomous, collaborative systems that exist on their own, and they also have their own source of data. So if one of them crashes, they can still continue to function. And I think the thing that is really fascinating to me is, as human beings, if we're going to make a plan to do something, like if you're going to go backpacking or you're going to go camping or go surfing or whatever, you go down this checklist, you make sure you have all your stuff, and you prepare in the event that what happens if my friend gets injured? Do I have anything in my first aid kit to deal with that? But yet, a lot of times when we go to design systems, we don't think that way, because we kind of think that software is malleable and it should just kind of work. But actually the opposite is true. It can be very brittle, especially when it's impacted by the way that we design it. So promise theory is by Mark Burgess. It wasn't necessarily for computer science. It's been applied to a lot of different disciplines, but I think it's really, really valuable to think this way when you're designing a system. So a promise is a declaration. It's an intent. I'm going to do something. It's a statement about what I am telling someone else that I can do. And the trust factor between me and someone else is the ability for me to deliver on what my promise is. So if you have a service that you're calling, right, you can actually track this and say, okay, that service isn't really reliable, so I need to have a backup service. And we had this in the energy industry. We had several services which we pulled weather from, and sometimes they weren't reliable, so we couldn't just not do our job. We had to pull it from another source and then kind of take a look at both representations and decide what was the best. So some of the key concepts: think in the terms of promises and obligations. And again, as human beings, if I obligate somebody to do something for me in order for me to deliver, then what I've just done is I've tied my ability to perform to their ability to deliver. So if they fail, I fail. And so ask yourself, is that how you want to live? Right? No, I don't think we want to live that way. We want to make a statement: I'm going to do X, okay? And that's where I'm going to stop at. I'm not going to rely on, person A, B, or C to help me do X. Now, I may need something from them, right? But I'm going to craft my environment such that if they fail, I can still deliver, right? So it's the way you're thinking about how you design your system. This idea actually comes from physics too. So autonomy makes information local, right? Leading to greater certainty and stability. So it starts out with a slimmer definition, but it ends up at a more realistic point, right? When you approach it this way. An autonomous service can only promise its own behavior, and obligations, on the other hand, diverge. Obligations will start: I'm going to obligate you to pick me up at 6 p.m. That's very well defined, right? You know it, I know it. However, from that point on, it diverges into uncertainty because I can't control you, right? Maybe you get stuck in traffic. Maybe you have a heart attack. Maybe you don't like me and you're not going to pick me up, right? Who knows what the issue is? However, if I make a promise to you and say, I will be there at 6, that's uncertain, but it converges on a more realistic outcome, because now it doesn't matter how I get there as long as I'm there at 6. So I think these styles of thought and this way of reasoning about software design helps us build systems that are much more concrete and can survive catastrophe and things like that. So, all right, so event sourcing. Event sourcing is, anybody in here not familiar with event sourcing? All right, good. So you know what it is. There's command sourcing, there's event sourcing, there's actually something in between called message sourcing, or whatever you want to call it. But the idea is essentially to pull in a command that was asked, validate it, and then split the results of that, if it's valid, into one or more events that you record. And I would tell you actually that in some ways, CRUD is event sourcing. It's 4 events, right? Create, read, update, and delete. The problem is the delete, right? You're actually altering history. So we'll talk more about that in a second. But the event sourcing obviously allows you to do a lot of interesting things. So some of the key concepts, and one of the really nice things about it that is very powerful in distributed computing is it's an additive architecture. So, you have some type of hash that's distributed, and you're always adding. So it's very, very fast to write. Whereas in a relational database or a more complex persistence mechanism underneath, you may have to do things like compound keys or synthetic keys and all these different things which make it more difficult not only to write but also to read. So for distributed systems, it's really, really a nice solution. Locks, very easy. There's very little locking going on when you're writing, right? And then if you use something like CQRS and you split the queries out to something else, then as you write, you can then throw that event over the fence, and you don't care what the outcome of that is. That's somebody else's responsibility. So you'll get data in, blah, 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 and this is why fast data and microservices can work really well together. You put that in another database and you store it in a read projection out of the box. So no longer do I have to do some kind of complex query to answer the question. The question's already answered sitting in the database. And I would argue that probably 97 or 98% of the questions that we would get asked, not as people but as our system is going to process, they're already known. It's very rare when you have a truly dynamic situation where people have to enter in, like you go to Google and you just type something in, right? In business, a lot of those questions we already know what they are, so we can highly optimize them and make them super, super fast. Yeah, criteria is tracked from inception, so one of the nice things about that is you can answer questions that may not have been asked yet. So if you're storing everything in these smaller events, and the context or the difficulty of question that you can answer is based on the granularity of your event model, right? So if you were to take a look at my life and you were to record something, say, once every week, then there would be a lot of data that you might be missing about me. But still, it's a lot better than if you didn't record anything at all, right? So again, the granularity of your event model is going to allow you to answer more complex questions. And this, obviously this looks like a checkbook. More mature business models, accounting, it's been around for thousands of years, okay? It's a perfect example of event sourcing. And on the right-hand side, you'll see a balance, which is kind of like the current state at the time of that entry. And that's just a optimization. So if somebody says, hey, what's your current balance? I don't have to go back and add all the events up. But I have them there if I need to do that. So you can kind of think of the balance column as a snapshot. So these more mature business models, they would never dream of storing data in a in a non-event sourced context. So if you call your bank up and they're just storing current state, every time you do a debit or credit, they change your current balance, and then you go to reconcile your checkbook and you're off, right? They say you have $20 and you say you have $10,000. You call them up and they say, oh, we're sorry, we don't use event sourcing, we use CRUD. So too bad, your balance is $20. That would be ridiculous. But yet we build lots of systems like this, if we're honest. So CRUD, we know what it is. We talked about it already. And I think CRUD is good, but I think you need to understand what it is. It's a relational model. Relational theory is really awesome. I like it a lot. I think it's very, very powerful. But ultimately, it's a current state model without logging, right? If you add, if you're using Hibernate or something like that and use Hibernate and VARs to do audit logging, then yeah, you do capture the log. But it's kind of forced. It's not the natural model that you get with a relational system. So, CRUD is essentially going to take a look at the change between 2 points. It's gonna, that delta, it's gonna take a look at it, and then it's going to persist that change and overwrite whatever the existing things are. So things like how that all works under the covers are often as a result of the underlying framework that's managing all that. They keep track in memory of the deltas for a couple versions, and then eventually they flush it out to the database. And under the covers, the database itself does that as well, because that's how you can do your rollbacks and everything else. It's got to keep extra data in there to be able to manage strong consistency. And I think the biggest challenge of it is that you're not really able to capture behavior. You're able to capture a very strong view of what now is, but you're not able to really learn about the behavior of something. And I think it was Jamie yesterday that was talking about behavioral programming. It's very interesting, event storming and behavioral programming. And I would argue that behavioral programming and those styles of thinking can be very, very valuable when you're starting to maybe rethink a design for a system. If you have an existing legacy system and you want to rebuild it, I think behavioral programming and those types of thought processes can be really helpful. All right, so here's your CRUD model, you know, your order line, shipping, et cetera. So we all understand that. So the next thing I want to get into is fast data. Fast data, again, is one of those terms. And what I would tell you is fast data, in a lot of ways, is about data in motion, okay? So we know about big data and OLAP cubes and data warehousing and all these concepts to take a look at data and get information out of it. Well, fast data is the idea is like, I can't wait that long to get my answer, right? I need it quicker. So we have this idea of data in motion. Is there any way we can use it to our advantage, right? Like electrical circuits work or anything else. And so I like Dean, you know, where data is processed as it arrives, leading to fast data systems that ingest continuous and potentially infinite data streams. I think one of the interesting things about fast data is fast data you have to apply temporal boundaries to fast data. Because it's infinite and it's continually streaming, origin and destination are now synthetic, right? You can move them around. You can say when I'm from 1 o'clock to 2 o'clock, or from 5 milliseconds to 10 milliseconds, or whatever. And that's a different way of thinking. We don't normally think that way, right? I think I get up at 8 o'clock the same time every day. It's a concrete time. But with streaming, that's not the case. And that thought process or understanding that ends up becoming very important. Colin talked about time series data yesterday. One of the things that I used to do was bitemporal time series data. So it's not just one time series point, it's multiple time series point for the same point coming in from different ingestion points, and then being able to reason across that and ultimately take that data to update what the current state is and also update what my predictive state is going to be maybe a couple minutes in the future. So that sounds really complex, but if you step back and think about it, it really isn't that hard when you think about, okay, I have the ability to set the destination and the origin, and I can move it around, and I can check my results, and if I don't like them, I can do it again. And we'll talk more about this in a minute about feedback loops. So fast data, we have really two concepts, real-time and near real-time. Most of us are beginning to embrace what we call near real-time. And that's anywhere from, you know, 1,000 milliseconds, 100 milliseconds to, you know, basically under a second. Real time is more like something you might do with high-frequency trading or something like that. But most systems, the far majority, can do near real-time analysis. So those boundaries, as I were talking about, end up becoming defined again by your SLA. And as I had mentioned, the temporal boundaries around it are synthetic, and it's something that you or the product manager helps determine how that data is to be used. All right, so feedback control. Feedback control, I think, is really, really fascinating, and it's a key part of streaming, without a doubt. And so the idea is I'm going to take a look at what's going on, and I'm going to constantly compare the actual behavior of my system to a piece of my system or the desired behavior of my system. I'm going to take a look at both of those things, and if I'm off, I'm going to make a change. I'm going to alter the flow to try to get that set point back to where I want it, right? And so these can be micro or macro in design. They're usually micro. So it's making these little teeny tiny decisions in real time or in near real time as your data is being processed to bring it back. And this is exactly how your thermostat works, right? You set it to 70 degrees, your house is maybe 68 degrees, it keeps making this check until it gets the temperature in the room up to 70. So the thing about feedback is it really doesn't require a lot of knowledge about the system, right? You have a very specific task, okay? For example, you go into Starbucks, they have a barista. The barista has a specific job. The barista makes coffee or whatever, they make. Where there's other people that do other things, right? The barista doesn't program, right? That's somebody else at Starbucks that's doing programming. The barista doesn't do accounts receivable. So he's making, or she is making very little changes to the process that they're working on in order to keep it where they want it. So that's one of the great things about it. The other thing is, in order to implement it, all you're doing is you're making a nudge, right? It's like, okay, because the impact is small, you can afford to be able to take some chances, so to speak. So I'm going to make a little nudge, and then I'm going to auto-correct when it doesn't go in the direction that I want. And the other thing is, I like this, is feedback systems are self-correcting in the presence of external disturbances, and that's the idea. You get, and if you know ACA and the supervisor pattern and things like that, that's in a way a kind of implementation of feedback control, right? You override the default supervisor, something occurs in a child actor, it bubbles up to the supervisor, and then you take corrective action. And that's basically a feedback loop. And it's a feedback loop that gives you the ability to be resilient or self-healing as opposed to fault tolerance. And that's, I think, a very crucial part about it. The other thing in this, as I had mentioned, you can take chances, you do little nudges, but you got to be careful that you don't push it too hard and you overcorrect. I think in these types of situations, especially like in computer systems or computer science, they're a lot less restrained. I used to think about, like, you look at a bridge or you look at a skyscraper and you think about, man, how did they build that, right? I'm still amazed when the phone rings and I'm talking to somebody on the other side. But you take a look at those structures, but one of the things about those is they're constrained. They know if there's bedrock underneath. They know if there's not, how deep they got to go. Maybe they can't build it there because of that. Or when you're building a bridge, they know the weather conditions. They know the current of the river. They know all these things. And they know the type of concrete that has to be used, how long it has to sit. So it's almost like a cookbook recipe. Where in software, what are what constrains and what we're trying to do. Right? It's this virtual world where we can play. So we have a lot more room to mess up and make mistakes. And so I think applying some of those disciplines from, the hard sciences to what we do can be very, very helpful. One of the things that I talked about was smoothing, or I didn't talk about, but you have data that's coming in. You have a predictive result that you want to project, okay? And because the data coming in may be erroneous, you have to take a look at it. So you have to set up a window and you have to say, okay, I just got a reading that said it was 2,000 degrees, and I know that's impossible because that means the house is on fire. So it's something's wrong, right? So you have to make a decision. You go to the data scientist and you say, okay, you're the smart person, go ahead and tell me how I'm going to deal with this. How many points can I ignore this 2,000 degree reading for? And she says, well, you can bring in 5 points, okay? And if the 5th point is still incorrect, then you got to raise an alarm, right? Because that means something's actually wrong. So anomaly detection becomes quite important. And one of the things that we can run into in these scenarios is alert fatigue, right? You keep, like, who here runs to save somebody when their car alarm goes off? Exactly. So that's another thing you got to be real careful of. So this is your basic feedback loop. You can think of this as a supervisor pattern, right? You have a disturbance that comes into the system. You're going to have a measuring element that's going to take that new reading and compare it to what the current set point is. If everything's fine, then you're done. Otherwise, it's going to go back, and a controller is going to then talk to an effector, and that effector is then going to go back after it makes an adjustment, and then it's going to do another reading. And so you're continually going through this loop, making these micro decisions, and that's how you stay where you want to be. So to recap on these things, we talked about these 5 different concepts, or 6 different concepts, which I think are crucial to building a distributed system. Microservices, promise theory, event sourcing, CRUD, fast data, and feedback control. These, if I were to sit down and say, hey, I want to learn more about distributed computing, I would go and I would study these 6 topics. So when we apply that to a system, we have all these components. What is a good system going to look like when we build it? So again, to recap on microservices, we have some rules there: promise theory, keeping your own data, keeping your code set small, etc., clustering, and so forth. So we start out with our system, and we may come up with something like this. So we have good microservice design. We have different services that are going to collaborate together, but they're autonomous. Some of them might have a cache. Some of them may have a database like Oracle or something because they need strong consistency. Other ones may have a NoSQL database or what have you, but they each have their own reality. And more often than not, each one of these databases may contain very similar or the same data, right? Now, let's say for the search service, I'm going to need a little information from my service on the right and my service on the left, but I'm not going to contain all their data. I'm going to contain just enough within that time window. Now, if I go beyond that time window, right, and those services are down for like 10 days, then the search service is going to have a problem. I'm going to have to start to say, these results are a couple days old. They may not be accurate, but I'm still telling you, right? I'm still responding, even though my answer may not be as good as we would like. So the other component we talked about, event sourcing, and here I do event sourcing versus CRUD. If you want to make a decision, if you care about auditing and history, I would use event sourcing. If you need to shard your data, right, and across a big system, I would use event sourcing. If you need strong consistency, or you only care about current state, then I believe relational and CRUD is an excellent way to go. So it's not which is better than the other. It's which is the right tool for the job. All right, so now we have our system. Our search service is, it's basically a cache that's going to get overwritten, so it's using CRUD. And our other 2 services, perhaps they use a relational database, whatever, or a NoSQL database. So we got that down. But at this point, we're still waiting for people. We're either going to push into the microservices or pull to get data into the microservices. We're still not necessarily processing data at near real time. And this is where I think streaming comes in and becomes really important. So again, just the components of streaming or the components of fast data is streaming. You got to remember these temporal boundaries. You also got to remember streaming or fast data is really orthogonal to microservice design. Now you can have a microservice that actually does real-time data, and that's many of them that I built have been like that. So I didn't necessarily have Kafka or some type of streaming mechanism embedded. I used akka or something like that. But not all microservices need to be built like that. And also, if you have something that's very valuable, like a really good queue or something like that that you can use, that all kinds of different services can pull or push into, then you should use it because it's a really great way to go. So now, this is the way I like to describe fast data. It essentially gives you the lifeblood or this data pipeline, or whatever you want to call it, this river. And all the microservices are little villages around the river. They all have different things. They may speak different languages. They may have different purposes, like one might be military, one might be a hospital, whatever it may be. They all have to work on their own. They're going to collaborate together. They're going to help each other. But if one goes down, that doesn't mean they all go down or whatever. And they all share data from this stream. Now, what I would argue is that stream should not be your source of truth, okay? Your source of truth is within your microservice. So you're going to cut a little canal, and you're going to run water in from the river into your village, right? And now you don't have to walk down to the river to get water, right? You now have water in your village. And so that's the idea of I'm going to own my own data. And I can then put back into this river, I can get in a boat and go down to the next village or whatever. So it's kind of like a highway, and all this data just consistently flows through it, just like a stream. So we could take a look at something like this. We've now added maybe Kafka or whatever, and so forth to your setup. So for the sake of time, I'm going to go a little bit faster and kind of get to the end here. So you have, I believe, feedback control is the secret sauce in a system. That's what gives you the ability to really pay attention to what's going on at a micro level. And then these other components, obviously are crucial. The thing that I want to get to here is we're almost there with our system, right? So now we have a Kafka, or we have this mechanism, so we have streaming data, real-time data that we can process. We have our microservices that stand on their own. They're collaborative and autonomous. And now we said, hey, we want to add some more features, so we're going to add machine learning and neural networks or statistical regression or whatever it is. We're going to add that in because that's also orthogonal to this. So it can kind of like poke into either the microservices or to the queue to get data and make decisions. We're not quite there yet. One thing that we're missing is the ability to have insight, okay? And so in addition to those components that we just saw, the last piece is being able to essentially have insight into our system. So who's watching the watcher, so to speak, right? The monitoring system is going to take a look into your architecture. It's going to report on things. And so you need in order to build a successful distributed system, you need all these components, right? And this is how you get a system that's resilient and elastic and all these different things. And so things like a mixture of Kubernetes and Akka is really powerful because Kubernetes gives you view into more of the hardware, where Akka is going to be at the application level. So if there's a crash, Akka can rebalance with the existing nodes, where Kubernetes can say, viewing network traffic is getting really high, I'm going to spin up another pod. And then it auto-joins with the Akka cluster. So I apologize for having to go so quick there at the end, but I wanted to make sure that we got through everything. And I wanted to save a minute or two if anybody has any questions. Yeah, just that way they can record it and everybody can hear you.
Very quick question. I was surprised when you said the stream is not the source of truth, the microservice is. Because it seems to me the microservice is taking from the stream on the one hand, and the microservice is more fragile than the stream by design. So could you?
Right, so if I were to ask questions about you, who would be the source of truth? You or what's on LinkedIn? It's you, right? And that's my point about a microservice. The reason the microservice is the source of truth is because it owns its current state and understands its own reality, and everything it either pulls or pushes is either historical, right, history, or it's hope for the future, right? So unfortunately, Kafka can go down, right? And if that happens, what, your microservice just, it can't do anything, right? It's got to be able to run on its own for whatever amount of time the SLA says it has to. So that's why I say the microservice is ultimately the source of truth for its reality. Awesome. Well, thank you, guys. Oh, yeah, go ahead.
With regards to the event sourcing versus CRUD, do you ever find it practical to employ both in a service?
Mm-hmm. Absolutely.
Okay.
Yeah, in many ways, if you take a look at event sourcing in CQRS, the query side is CRUD, right? You may store it in a relational database, but you're basically overwriting your projection, your view projection, right? Because you wanted to optimize it and push it out. You know, MySQL became so famous because they stopped normalizing their structures. They flattened everything out, and they had these really long tables with a lot of columns in because they couldn't pay the price of the joins, right? So I would argue in event sourcing and CQRS, event sourcing is, the right side, that's your event sourcing, but the read side is actually, it's basically CRUD. You're going to create a new record. You're going to overwrite an existing record. And you don't care because the great thing about that is you can always recreate that reality because you have the historical view on the other side. Great. Well, thank you guys for coming out.